Hello everybody and welcome to CS302 Online. Hope you all had a good weekend, ready to learn more about data structures. And today we are going to be talking about some data structures. In fact, we're going to be talking about linked lists, stacks, and queues. So let's begin. All right, so last time first of all, recurrence relations, we're done with that. We've moved on to other greener pastures. We may revisit that randomly someday if I choose to, but at least for now we're done with that. So now that we understand asymptotic complexity, we can analyze asymptotic complexity of some of the stuff we already know, such as linked lists and stacks and queues. And so, and even if you don't know stacks and queues very well, if, for example, if you took 202 for the summer or things like that, then we will go over it a little bit in detail. But really what we want to see is to get a better feel for figuring out the asymptotic complexities of algorithms. And so last time I started by talking about the asymptotic complexities of the major operations with an array, which are insertion, deletion, and accessing, right? And so that's pretty much what we kind of finished off last time, right? We said for the insert, with the arrays, the biggest issue that you have is that if you're trying to insert something in the middle or in the beginning, you have to like shift everything forward, right? In fact, you might even need to like shift everything by copying it into a new array if the array is completely full when you're trying to insert something, right? On the side of accessing though, searching, of course, can take n time, or if the array is sorted and you use binary search, then you can lower that down to logarithm of n, log of n time. But in general, we also like to say that accessing information on an array is O of 1 because we're saying if we want to access like the nth element, how long that's going to take. And that, of course, we can just put in the index, and we get it because of how pointer arithmetics work and how arrays are stored in C++, which are basically just contiguous blocks of memory, and you can just do basically shifting or arithmetic, basically, like, plus 12 in an integer array would be basically 4. A12 would be the third element in the array, okay? And so deletion, on the other hand, we're making the assumption that we already located what we want to delete, and in that case, how long is that going to take? Of course, if we want to like completely erase it and like shift everything back, that could be O of n. But if we just simply want to mark something as deleted, then it could be constant time because we just basically replace it. We can get there immediately and whatnot. So anyways, how does that come into play with a linked list? And that's what I want to start talking about. But before I do, let's go ahead and do a quick review on how linked lists work, okay? And hopefully you guys remember it from 202 because we don't have enough time to like go that into it like super into like how to actually code a linked list. But of course you will get that review when you're doing the assignment. So right now I'm mostly concerned about the conceptual idea of a linked list. And so a linked list is typically made of nodes, right? In fact, all of these nodes are linked, which is where the name linked list comes from. And there's two main kind of linked lists that you usually talk about. And those are the singly linked list and the doubly linked list. So let's go ahead and first look at the singly linked list. Okay? And I hope you guys are all here. So 25, okay, cool. Yeah, so we are live. Nobody said anything, so like I want to make sure that people are live. All right, so there's two major components in a node. So a linked list is made up of a bunch of nodes, and the nodes themselves can be split into two parts. And those two parts are going to be the data component and the link component. The data component tends to be either some data type, which can be a class even, an object, or something built in, but it doesn't have to be the actual data being stored there. Like, yes, you could make that like an integer, but you could also make that a pointer to something else. So you could make data be a pointer to like actual data that could be bigger, an object or whatnot. Or you could actually store the data itself there. It really depends what you want to do. However, in the purest sense, you typically just think of that as like the data being held there, okay? The other part of the linked list is going to be the link part. The link part is typically a pointer. In fact, not typically, I would say pretty much every single time it's a pointer. And it happens to be a pointer of node type. So whatever the class or struct, which same thing, remember class and structs was the only difference. Structs are public by default, classes are private by default, but in C++, that's it. You can change that very easily with a modifier and basically do the same thing. It's more of the word struct kind of comes from the C side, and that's why it's still there in C++. But anyways, essentially, when you create this as an object, as a class, what you're making link is a pointer to that same class so that you can point it to another node, right? And that other node is also going to have a data and a link component, right? Now, typically, your linked list being made up of multiple nodes, one way to signify that the specific node is the last node of the list is you make it point to null when that's not pointing anywhere, right? Okay, just to briefly refresh your mind on how that is actually built, you could go ahead and say class node is, and then you put in the constructor. I like to put a constructor always in these because what you can do in that constructor is you can initialize the link component to be null, which is a pretty good practice and helps you avoid like headaches. So let's just make everything public. Don't ever make your constructor private. That is going to break some things, unless you know what you're doing really. But yeah, so let's make the link component. And another name for a link that you typically will see, at least I love using it, is the word next. So I like using next instead of link, but whatever, doesn't matter. You can call it potato for all I care. Although self-commenting code is a good thing to do. And then your data component. In this case, let's say that we wanted to make it a template. You know, that's probably a good practice to do so that it's flexible. So then we can just make it T data, right? If I remember my templates right, I think that's good. I haven't done templates in like a month and it kind of went away, but I think that's good. So yeah, what's a template? A template is a keyword in C++ that allows you to do compile time polymorphism. What that means is instead of declaring a specific data type for a function or a class, there are function templates and there's class templates. Instead of requiring you to do one of those, like to give a data type, like for example, suppose I have a function foo, right? And my function foo is supposed to add two components together. So I got an int x and an int y. And the purpose of foo, in fact, maybe let's not call it foo, let's call it add. And let's make it valid returning, so int add. And the purpose of this function is literally to take x and y and add them together and return that value. That's my function add right there, okay? This function is amazing, best function in the world. You love it. It's so amazing that you are gonna make the same thing for doubles. What do? You copy paste it and then you change the word into double, right? No, you make it a templated function. Templated function is basically gonna work for any data type that you throw in as long as the operator works for it. So what do? I put the word template up here. I put the little less than and greater than signs. I can put the word type I think it's called type something with the word type in it. But you could also use the word class and the word t, and that'll work too. But there's another one. I think it's called type name. Yeah, type name. You can use type name t or you can use class t. Either one will work. There is technically a difference, but I can't remember it, and it's pretty insignificant for this level of knowledge, anyways. But yeah, so you put the word template t, and now you replace the word int with t. And so now you could pass into this function two doubles, two strings. They have to be the same type, but you pass two doubles, two strings, two floats, two notes even. And as long as the plus operator works, then you're good to go. Now, of course, the plus operator is not going to work with non-built-in data types, But you can do operator overloading, which I'm not going to go over. You can check my YouTube channel if you don't remember it. And then you can basically overload the plus operator to work with anything. So like for the node, you might want to actually add the data component, but not the link component, right? So anyways, quick review on templates. So if you want to know more about templates, you can check out my 202 videos over the summer and then search for the one on templates and just watch that. Probably the easiest thing to do. Or just go on Google. Go Geeks for Geeks. They have a thing on templates too. Function templates and class templates. They're great. They save a lot of time when you're coding. Make your life a lot easier than to have to code the same function like 50,000 times. And then you forget, you remember you have to do something and now you gotta change it in all the 50,000 versions of it. Or you can just have one template and like relax, you know. So anyways, we're making our node templated. And so we got the data component, we got the next component, and now we can go ahead and do our constructor. So for the constructor, I'm not gonna, I mean I could, yeah, I'm gonna make it require actually the parameter for the data. So we can't have like a blank node. You don't have to do this part, but I'm gonna do it. So, or do I want to do it because it's templated? Yeah, I'll do it, why not? So you gotta pass in a parameter which we'll call, you can actually call it data too, but that might confuse some people, so we'll just call it D. And then we'll just say that data gets initialized with D. And then also next gets null. Like that. And then the actual body of the constructor doesn't even need anything in it. So yeah, you can do that. I don't think you need the word template on top of the word node because it's an inline constructor. If it was outside of the class, then you would definitely need the word template on top of that as well. But anyways, yeah. So now we got a constructor and we got the two components of our node class. And now, of course, we can create a linked list class, which can have some of the important operations that we talked about, such as insert, delete, find. Of course, delete what kind of delete do you want? You might pass in something to search and delete, or it can just be like delete a certain index, and so on. In fact, there are two main kinds of linked lists that you typically see, and it's actually worth pointing out. There's ordered and unordered. Unordered is kind of like YOLO, where you just kind of throw things in and whatever, and you can put them wherever you want. You have that freedom. On the other hand, ordered, you don't actually have control over things get inserted. They get inserted based on a certain criteria. The most popular one, the one that you probably covered in 202, is sorted in the sense of ascending order or descending order, where you insert something into the linked list and it's going to put it in the right spot alphabetically or numerically, ascending or descending, okay? So in that case, you have an insert function and it takes care of locating where it has to be inserted and then dumps it in there. And then vice versa for the delete, it's just like you say delete a number and it'll search and delete that number if it's found. But you have no control over where things are put in or out. It's the more nice version of a linked list, I suppose, than the unordered, which is just like whatever. So it might be actually worth looking, because like I said, I don't have time to go over so much code, but it might be good looking at the insert function, because that code will kind of cover most of the cases of like what you do with a linked list in general. So suppose that we were coding some, we have to have a class. So let's say, and the class would have to be templated probably because we made the node templated, but whatever. You have a class called linked list, and somewhere in that class, you are going to have your insert function, and your insert function is going to take a value that is templated, that is representing the data that you're going to insert into your linked list, okay? And we're doing the order version of that. And so what you need to do there is you need to first locate where to insert and then actually try to insert. And so to do that, you are going to have to consider 4 possible cases. Can anyone think of the 4 cases where you could insert in a list? And there's 4 because it's a special case. It's mostly like 3 and the plus. So If I'm inserting in an order list, and it doesn't have to be linked list, just in general, if I'm inserting into a list that is sorted, some data, what are the possible scenarios of where I have to insert that I have to consider? I'll give you a hint. One of them is inserting right in the beginning, right? Okay, here we go. We got some people responding. Cool. So we got empty list, at start, at end, or at middle. Yeah, you pretty much got it. Indeed. Second person, empty list at the beginning, in the middle, at the end. You're right. Yeah, you guys both got it. Well done, well done. So yes, we have the special case of where it's an empty list and you're inserting the first thing, basically. Then you have the other three cases where it's not empty. And as you all said, it's basically inserting at the start of a non-empty list, inserting at the end of a non-empty list, and then basically, I know we call it middle, but basically anything else, right? Because like it's the second item all the way to the second to last item, right? So that's what we really mean by middle, but you guys get it. So if we're trying to write code for this, you know, the first case is like the easiest because like, I mean, it's an empty list, so you just make a brand new list, right? The other cases can be a little bit tricky, but the start and end one are nice because you only have to deal with one node, right? Because if you think about how a linked list is built, which again is made up of those two components, you know, if you're inserting at the beginning, you know, this is, let's say this is the node you're inserting, okay? Here, let me make it nicer. That's the node that you're inserting. If you're inserting at the beginning, it's as easy as just dumping it there, right? Or if you're inserting at the end, then you can just put it there. No problem there. Inserting in the middle is a tricky one because first of all, you got to break some links, you know, move some space, and then put it in and link things back together, right? So that's kind of what I want to show you because if you understand how to do the insert, you can pretty much do any other operation in the linked list. Delete is basically this, but backwards, even easier actually, technically than insert. So that's why I want to try the insert one. So anyways, we'll make some assumptions as we go of some sort of variables because here's the one thing that a linked list should always have, okay? So you have nodes, sure, but even an empty list has one thing that you always need to have, and it is a pointer of the node type. And that pointer is typically called the head pointer, okay? So we need a head pointer in a linked list. What is the head pointer for? The head pointer is, as the name implies, pointing to the head or beginning of a linked list. And this is a singly linked list. Now there's also a secondary pointer that is useful to have, albeit not necessary, and that is the tail pointer, which typically points to the end of the list. Now, the end game of me explaining you linked list is to look at the asymptotic complexity. The tail pointer is going to help us lower one of the asymptotic complexities from O of n to O of 1. So that's a big difference. So that tail pointer is useful. I would say it's a good value because sure, it takes more space in memory. You have one extra pointer in your program, blah. But technically speaking, you get a lot of savings for it. So it's a good value on that. Okay. So anyways, let's so we're assuming that inside our class we are gonna have essentially a node pointer called head and a node pointer called tail, and they are initialized to null in the constructor of the class, okay? Or technically, if you're doing C++11, that actually would compile and run just fine. You could just literally do it when you're declaring it too. Only C++11 or after would work. Okay? So anyways, we have our class, and we're going to do the insert function at some point right now, and then somewhere in there's those variables. That's the only actual variables that you need in the linked list class. I mean, it might be nice to also have like a size function, or sorry, not just a function, just a size variable, because it's nice to know how big a list is, but not necessary. It's like just like extra stuff. Really, the only things you need are the head and the tail. And again, tail is optional for improvement in efficiency. Otherwise, just head. In fact, with a single linked list, you definitely need a head. But with a double linked list, which is I was going to talk to next, you can actually just get away with having just a tail, which would be weird, but would still work because of the doubly linked nature. Might as well actually talk about double linked list now before I do the insert, because then I can kind of make some comments as we go. So a double linked list is a linked list with one extra component, and that is going to be, you still have your data component and you still have your link component, which I like to call next, but you have a secondary link component behind the data component per se, which actually points to the previous node, and I like to call it preb for previous. And so I have preb with a V, I have data, and I have next. Next points to the next node. Data is my data that I'm holding there, typically templated, and previous or preb points to the previous node. So a doubly linked list, as the name implies, doubly, means that every single node is connected to two other nodes, with the exception of the first node and the last node, which, by the way, same thing goes for the singly linked list. For a singly linked list, every node is connected to one other node, ahead, with the exception of the last one, which is not connected to anything because it's at the end of the list, right? So that's the doubly linked list. Just thought I'd mention that right now. But anyways, going back to the singly linked list, let's go ahead and do the insert function, okay? So we got insert t data like that, okay? And so I really should have gone with the IDE today and coded there. It would have been nicer, but whatever. We're not gonna go full code on this. So the first thing you want to do is you want to create the node, right? So let's go ahead and make a temporary node, call it temp. And you use dynamic memory allocation. So you say new node, and then in the constructor, you're going to put the D for the data because that's what we did. And we don't need to worry about setting the next component to null because the constructor does it for you. So hopefully that's starting to convince you that it's always a good idea to use your constructors to initialize pointers to null. Okay? All right, so we got a node. It's just kind of floating in cyberspace or whatever. Oh, by the way, I do like to use this little circle like that when I'm using in pointers. That signifies to me null. Okay? So if you ever see me draw an arrow with a circle like that, it just means that it's currently set to null. And it is, so, because the constructor. Okay? So just wanted to clarify that. Okay. So how do we know if a linked list is completely empty? Well, as I told you, you want to initialize in your linked list class the head to be null when you first run your program, which signifies that a linked list is empty. Anytime your head is empty, anytime your list is empty, your head should always be set to null, and hopefully your tail as well. But that's not as super important. But I would say it's a really good practice. Okay, so you can just put an if statement and say if head is equal to null. You could also use null PTR if you're using C++11, but I'm just going to use null. Then that's a sign that your list is empty. Okay, in that case, that just makes our life easy because all we got to do is basically set the head, if I can spell head correctly, to be equal to the new node that we made, which is called temp. And we're done. Actually, no, we're not done because this version of our linked list is going to have a tail. So we also need to set the tail. So in that case, I will also set the tail. In fact, I can be hardcore and make this whole one line of code technically. So we'll do that. Tail equals head equals temp. That will set both the tail and the head to basically, we'll call them T and H, to point to the new node that we've made. Okay, so that takes care of the first case. Three to go. Okay, of course we did the easy one first, but then again, it's always a good idea to start with the easy stuff first. Okay, so I suppose because I'm lazy and there could be better ways of coding this, but I can't be bothered on the fly to code them. I'm going to put a return statement there at this function so that it doesn't go into bad areas, okay? You could probably better off using like an if else kind of situation, but I don't want to have to like tap the code forward, because I have limited space. So yeah, okay. Don't try this at home, kids, kind of thing. Okay, with the whole like multiple returns in the same function. It's not good practice, but whatever. All right, so other scenario that we are facing here, if we're still inside this function, is that the head is not equal to null. Okay, in that scenario, we need to identify the location to insert at. Okay, now this is a good review of how to traverse a linked list. There's two main ways to do it. One way is recursively, and the other way is iteratively. Recursively, I guess we'll take a little bit of an aside. Let's say we wanted to make a print function for our linked list. Is what you do is you pass in the head to your print function. So the parameter here is going to be a node pointer, okay? And that pointer is going to be the head. So you're going to call the print function with the head as a parameter, that head address, okay? And first you want to have your base case in recursion. Always check your base case before you do your recursive case. Otherwise your recursion is going to go forever, okay? So your base case is basically whether you are printing an empty list or you finish printing the list, which essentially is both going to be if t is equal to null. If that is the case, you're done. Return at that point. Don't try to dereference something that is pointing to null because you will sack fault pretty quickly there. So otherwise, you're not done. So you want to go ahead and print out the current component there. So you can say t data. Don't forget to use your arrow operator because this is a pointer we're dealing with here. By the way, good refresher, if you ever have a situation where you have code that is in this format, if you don't want to use the arrow operator, you can do this, but you have to use the dereference operator. However, the situation arises that the order of precedence in C++ says that the member access operator has higher precedence than the dereference operator. So this is first going to try to do this part here, and then it's going to dereference that, which is going to be garbage. We want to make sure we dereference the pointer, and then that gets us basically an address pointing to the first variable of the class, and then the d part's kind of like the shift in that to get to the right variable. Okay, so like for example, if this object is at address 100 and then d happens to be the third variable in there, then it would probably say d plus 12 or something like that. Well, not 12 because it's hex, so it would be like b or whatever, but you get the idea. And so essentially that's what we want to do, and for us to do that, we need to first get this address. And so because of order of precedence, what we need to do is we need to put parentheses like that. Okay, so that's just a quick refresher that because this is just like kind of nasty looking code, the C++ gods blessed us with the arrow operator. If you have something of this format here, the equivalent, I guess, let me just put a different letter of that would be t.d.w, but first you would need to dereference this part, and then you need to dereference this part, and it would be like Inception with the parentheses. Okay, so again, if this is rusty for you, I'm pretty sure by the time we finish this semester, you will not be rusty with it because you'll have to use a lot of stuff. But hey, actually, you don't technically need to use the parenthesis stuff because you can use the arrow operator. So it's more of like if I, for some reason, decided not to use the arrow operator in my skeleton code, which I don't think I would have, but then again, sometimes I just write those at like midnight, so whatever. Anyways, going back to the recursion, we of course are using t-arrow data because we didn't want to go with the weird dot and parentheses stuff. So this, of course, is going to print out the current element, and now all that is required is the recursive case, which is basically to go to the next spot in the list, which means recursive call. So call print on the next item in the list. So not t, but t next, assuming that the next pointer is called next or link or whatever. And that's it. That should take care of us. By the way, little quick quiz. What if I wanted the list to print backwards? What change would I need to do? It's a very simple change to make this function print the list backwards. So suppose I wanted to write a function called print backwards. What modification in this recursive code do I have to do to change that? Call print before cout. You are indeed correct. Very well done. Very well done. I'm proud of you for that. So yes, all you got to do is you got to move this down here. And in 326, when they talk more about recursion, they're going to, well, not just recursion, but grammars in general, they're going to talk about the concept of head and tail recursion. And that's basically what we're fiddling with here. what we had before will be considered tail recursion. This is considered, I believe, head recursion, because the action is happening before the recursive call in head, and in tail, the recursive call is happening first, and then the action that is happening, which is the CS statement. That is not to be confused that you might think like head recursion means that the recursive call has to be the first thing in the function. No. Always, even in head or tail recursion, your base case is always first, because otherwise the whole thing explodes. And by explode, I mean it will like recurse forever until you Stack Overflow and whatnot. So yeah, well done. Okay, cool. All right, so little refresher on recursion, and by the way, what is the recurrence relation of this? I believe it would be probably t of n minus 1 plus 1, something of that sort, because you're just going one by one in both cases here, by the way. I suppose this might be like that or whatever, but yeah. Okay, so all right, anyways, going back to the insert. So in this case, we're not going with recursion for this, because it's part of a function and we don't want to do other functions. So we'll do it the iterative way of traversing a linked list, which is with a while loop. So what I'm going to do is I'm going to create another pointer in this function, local variable, and I'm going to call that the current pointer, which I like to use the word cur, and I'm going to set that to the head. The reason is because I don't want to modify the head variable. The head variable is very valuable to me because it always points at the beginning of my linked list. I want to start up with that, but I don't want to mess it up. So I make a copy of it and I deal with the copy. Okay? So that's basically what this line of code is doing. All right. So now that I got a copy of this variable, which I'm going to kind of call like my iterator, is I'm going to go ahead and put it in the loop and say, well, cur is not equal to empty. Or no, not empty, but yeah, you get the idea. Okay, so now I am looping. Well, here I'm not technically looping yet. So the way I'm going to loop is at the bottom of this, I'm going to say cur equals cur next, and this actually mirrors very much what we did with the recursion, with the recursive call t next, because this is going to update my current pointer to first point to the first node here. Where's my arrow? And then point to this one, and then point to this one, and then point to this one, right? Because if I was to write to you, if I have cur, or here, if I have head, right? And well, instead of next, I'm going to put n, okay? Because I don't want to have to type the word next. If I say this, which of the nodes is that pointing to? Well, this is head next, this is head next, this is head next. So yeah, so that would be the fourth node, technically speaking. Okay, so and then of course if I after that did like D for data, then that would be yes, this data technically, I believe. So head next, head next, head next. Yes, yeah. So that would be that one's data. I want to make sure I wasn't lying to you. So yeah, okay. All right, cool. So going back to the insert function, so now we have created this little loop that's going to go through each of the nodes and just kind of keep going until it gets to the end and then gets out of the loop, okay? So what we need to do in this loop now, and this is actually, we're actually going to probably need more space. So let me copy this beneath. I'll leave that one like that, but I will still copy it again here. We're going to have to throw in a bunch of code in here, so let's just scroll that like way down there, okay? So in here, we want to check if the node that we're looking at compared to what we have is greater than or less than, okay? Now, this matters if you're inserting in ascending or descending order. For now, we're going to say that the linked list that we're working with is in ascending order, or better yet said, non-descending order, right? So non-descending order, that's like the politically correct version of ascending order, because technically that covers a situation where if every single node is the same item, like equal, like you just have a list of all fives, technically speaking, that's not ascending order or descending order. That's just like a weird situation, right? So by saying non-descending order, we mean ascending order plus the weird case of everything being equal, or just duplicates in general appearing. So it's a nicer term to use, okay? So FYI. I don't typically use it, but I do like to point it out so that you are aware of it. So anyways, we're doing ascending order, okay? So in ascending order, how do we know if this is the spot to insert? Well, we can check with an if statement and say if the current item's data, if that value that we're looking at next, if that value is less than temp's data, which is the one we're trying to insert, I believe it's called temp, I forgot already. Yeah, temp data. That is a sign that we have to insert before it, right? Because what we're saying is the value that we have is bigger. Wait. Did I say this backwards? Hold on a second. If current data is smaller than temp data. Hold on, I gotta think. If temp data is greater, yeah, no, this is right. I just wrote it backwards, which made me confused, but I think it makes more sense. I mean, I wrote it right, but like if I flip it, it might logically make more sense to you. So I'll do that because it made more sense to me brain-wise. So like if I move this here and here, but I flip the sign, then it makes more sense when you speak it in English. If the data that we're trying to insert is bigger than the data that we're looking at right now, that means that it would have to go after, right? Because it's bigger. On the other hand, if the data that we're looking at was smaller or was actually greater than what we're currently inserting, then we have to keep going, right? So, for example, let's say, let me put numbers to this. We have 5, 7, 10, and 12. And we're trying to insert 3, okay? We're trying to insert 3, okay? So, we're saying if 3, and we're looking at 5, if 3 is greater than 5, then that means that we would have to keep going. But it's not. 3 is smaller than 5, right? If it's smaller than the current data, then that means that we can probably insert it here. Okay? Because otherwise we would go over. Okay? So for example, suppose that we were also inserting 8. Okay? 8 is bigger than 5, which means that it could go anywhere after, but it definitely does not go before, right? Because if it did, it would be smaller. It could go here, it could go here, it could go here. I have no idea what it's there because I can't see it yet. But I do know for a fact that it has to go after the 5. On the other hand, with the 3, it cannot go anywhere else but before the 5, because if the 5 is bigger than the 3 and I try to put the 3 after the 5, it's going to break my ordering, okay? So based on that logic, I can either leave the code like it is and then write the 2 cases for when it's going after, but I'm actually going to go ahead and write the first case for when it goes at the beginning, okay? So I'll flip this again one more time like that and leave it like that, just so I can do that case. So in this case, it means that it should go at the start, okay? However, by start, this could be like the 5th iteration in the loop, right? It could also be like the end of the potential loop or whatnot. So I gotta be careful about how I do that. So first of all, I need to take temp, next pointer, which is currently pointing to null, and I need to set that to point to cur, okay? So what I'm doing is, if I have my linked list here, what I'm doing is I'm taking the one I'm inserting and I'm updating this pointer here to point to the cur, which is the one that it should go before. Okay, so I'm linking them together. Okay, next thing I need to do here is figure out, is there something before that I have to worry about? Like, Am I linking this from the beginning of the list, or am I not? So if I was to be linking it from the beginning of the list, that would mean that cur would have to be equal to the head. If that was the case, then I would know that this was the previous beginning of the list. If that's the case, all I gotta do is update to make this the new head. So like before it was like this, now I gotta go ahead and replace that with this, okay? So the way I'm gonna do that is I'm gonna check and say if cur is equal to head. If that is the case, then I know it's the beginning of the list, so I can go ahead and set head to be equal to temp, okay? Otherwise, I don't want to do that. However, if that's not the case, then it means that there's data before me, right? So it means it wasn't the beginning of the list, potentially. If that's the case, then what I need to do is I need to update the previous pointer to point to me, okay? However, I don't have access to that previous pointer the way I have this coded right now. I don't have a previous in here. So how do I do that? Well, there's two ways. You could be doing cur next and change the whole way that I have this, or I can just go ahead and create a previous pointer, which is what I'm gonna do to make my life easy. So I'm gonna go ahead and create another variable here called previous. And initially, I'm going to go ahead and set it to, I could set it to null, but I'm going to go ahead and also set it to head. This is the part where I wish I was coding on the computer, so like we can debug checks this. But anyways, so now the way I'm going to do this is I'm going to make prev get cur before I update cur to next, which means prev is always going to keep the pointer to the node before current. By doing that, then I can go ahead and say else prev next gets temp. This line of code is what it's going to do is this. Prev is now always lagging behind by 1. So like if cur is pointing there, prev is pointing there always, okay? And if I'm inserting in the middle here, you know, I can easily point the current node temp to cur by saying temp next gets cur, which I already did here, right here, okay? But now what I need to do is I need to change this from linking to there to linking there. That's easy because I have prev, so I can just say prev next, which is this part, gets temp, which is what I'm doing right there, okay? So now this takes, this takes care of the situation where it's in the middle, but also where it's potentially in the end too. Because here's the thing. The only thing here that would be different if I was at the end of this, like if it was the last thing I'm inserting, so like suppose that I'm trying to insert at the end of the list, is that cur next would be equal to null, right? And in the, yeah, that would be equal to null. I don't think I have to worry about that, right? I think this is good. Let me check. So we got temp is less than data. It should be a start. Temp next gets cur. If cur equals head gets head temp. Otherwise prev gets temp. Yeah. Yeah, okay, so I guess the only thing I have to worry about now is actually if temp was greater than cur, such as a scenario where I still haven't inserted after the loop. Yeah, so I do have to worry about that scenario. So like the biggest number I'm trying to insert, which will actually be at the end, yeah. So that will not still be inserted. Once again, if I happen to go into this part of the loop here, of the if statement, I suppose, just to make my life easier, I'm gonna put a return. That way, if I ever get out of this loop here, that means that I have not inserted yet. But that also means that not only have I not inserted, but this must be clearly the last thing that I have to insert because it's the biggest number or whatever. In which case, I can easily insert by saying prev, which should have, because cur is going to have null right now because it reached the end of the list. So prev is going to be the last item currently so far. So prev next is going to get temp. And because temp is already pointing to null, I don't have to worry about that. I do want to update the tail though to point to temp. And by the way, actually, technically speaking, I could also, instead of doing prep next, I could have done tail next gets temp. Okay, that would have worked the exact same way because I have a tail, technically speaking. But yeah, that's pretty much your insert function. I don't think I have a bug, but it's possible. If I did, probably a typo or something. But this is pretty much the heart of how you would do this. Yeah. Yep, there's better ways of doing it without the multiple returns, but the way I did it is just going to avoid bugs. Basically, the typical bug you find if you don't put the returns in the right spot and you don't refactor the code to not require them is you insert once and then you insert again. Like, for example, I insert once in the loop and then I insert again at the tail and like it breaks things. So you want to make sure you're careful about that. But other than that, that is pretty much how that works. Okay, so hopefully this kind of refreshes your mind on how linked lists work. So now going back to the purpose of the class, let us look at the asymptotic complexity of this operation. Let's start with the insert, okay? So what is the asymptotic complexity for inserting? Both for omega and for big O. Best case, worst case. What do you guys think? O of n omega of 1. So you're claiming that it will take O of n for the insert and omega of 1 for the insert. I would say that you are indeed correct, because which of the 4 cases, in fact, here, answer me this. We have the 4 cases for the insert, right? Which of the cases, if you analyze each of the cases, what's the asymptotic complexity of each of the cases? So, of the 4 cases that we have, I can go ahead and go back up to them. What will be the O of n of each of those individually? I know that the overall is O of n for the whole thing. You are correct in that. But which of these will give you O of n, and which of these will give you the omega of 1? And what about the other 2? Yes, you do have to loop through it to the end. So that brings up the point. So inserting at the end, this one is definitely where the omega of n is coming from, because we have to go to the entire linked list, run that while loop literally all the way until cur is equal to null, to insert. So the O of n is definitely coming from the inserting to the end, or at least from that is partially coming. Omega 1 is you insert immediately. That is correct. So omega of 1 would be where you have basically an empty list and you're inserting there. Okay, what about these 2? What are they going to be? Insert at start and insert at middle. Let's just say for the sake of purposes that middle means like exact middle or something. Insert at start would be omega of 1. Yes, you are correct. It's still constant time. And then insert at would give O of n. You are indeed correct. It would also give O of n. Technically speaking, it would give n divided by 2. But we, of course, know that that's the same thing as O of n with a constant of 1/2, right? It's a certificate. Plus, technically, middle could be the second to last. So it could be like n minus 1 or something, which would still be n, right? With pretty much any constant bigger than 1. So, yes. So that's important to understand, that when you're trying to analyze what the time complexity of an algorithm is, you don't have to like look at it and just kind of figure it out in its entirety. You can break it down into the different parts of it, the different sections of the code, and analyze the asymptotic complexity of those individually. And now that you're looking at that, you can be like, well, the smallest omega we have is this one. Well, these are basically the same thing, but I'd say that this is potentially, no, they're about the same thing. So I'd say, yeah, both same thing. And then the biggest one is definitely this one with a close follow-up by this one, right? So that's how you would come up with the omega of 1 on the big O of n as well. Okay? So great. Now that one we did by code, but now this one we didn't do by code, but I still think you guys can figure out. Delete. So the delete, there's 4 cases again, right? For the delete, because I said it's basically the same thing with backwards. You're deleting from an empty list, which basically means you don't delete anything. You are deleting at the start, and then for the other ones, it's not empty. And you're deleting from the start, from the middle, quote unquote, middle, and then from the end, right? So what are going to be the asymptotic complexities of this one for the delete? Still omega 1 and O of n. Right, but what about like independently of each of these? Like which of the, you know, we'll call this 1, 2, 3, and 4. I want to see those. What is 1? What is 2? What is 3? What is 4? Empty list and start is 1. Yes. And then empty list is 1 omega 1. Okay. And then well, I'll just put it. Middle and end are going to be again n. Okay. So yes, you guys are correct in that you can say that that is the case. Okay. For the delete. Finally, for the access, I'll just tell you that access, you got to identify what we're doing, which is the same thing we're doing with the insert and deletes. So then you would say that they are also potentially O of omega of 1 or O of n for accessing, okay? This is all for the ordered version. However, if we are talking about an unordered linked list, whether it's a singly or doubly linked list, suppose that I told you you had to delete. At start, at middle, at end. Just those 3, okay? Don't worry about the whole being list empty. If I said an unordered linked list, which means I'm telling you the location that you gotta delete, you don't have to worry about finding it potentially. I could tell you, you gotta delete, let's say that there's 10 items in my list, okay? You gotta delete the first one for this one. You gotta delete maybe like the 6th one for this one, and you gotta delete the 10th one for this one, which is the last one, okay? What will be the asymptotic complexity for deleting from an unordered list in this case? What will be this one, and this one? I can actually, I'm gonna go ahead and throw in a, so wait, don't answer. Answer the first 2, but don't answer the last one. I'm gonna put in a Twitch quiz for that one. New poll. Last poll was, will it work or sec fault? That's funny. So, what is the asymptotic complexity of deleting at end unordered list? I can't put the last part, but you got the question. Unordered list, okay? And I'm going to put a couple of them. Duration 1 minute. All right, so I put a poll out because I'm curious what you guys will think. So the first ones, while the poll is going on for 1 minute, please vote. Let's go ahead and see what you guys said for the first one. So the start on empty is omega of 1. So, oh wait, no, that's the previous one. So start is omega of 1, middle is O of n. So I do agree with you that this is 1. Because you can use, well, I'll tell you why in a second. And I agree that the middle is n. I agree with that. Now, this is the big question. So, poll, let's see what the results are so far. Ooh, this is good. I like this. I'll share it on here, the results. It's anonymous, so don't worry, by the way. I don't know who's voting for what, so it's anonymous. So feel confident. Okay. So that was a good question to ask at the end, because that's the whole point of this. Yeah. So this is the results of the poll. We had the winner, or the people that voted the most, was we had I'm blocking the thing. So we had 17 people vote for n. We had one person vote for 1. Okay? And then nobody voted for log n and squared n, which of course were all just, random ones. But okay, so here's the thing. Neither is wrong and neither is correct in its entirety. Because here's the catch. You have to make the big assumption that you asked last second, right? Does this unordered linked list have a tail pointer or not, right? Because here's the catch. If it has a tail pointer and you know for a fact you have to delete it at the end, you just can go ahead and delete with the tail pointer, right? You can just go ahead and say tail and then bam, delete it, right? But vice versa, you might say, well, I can delete it, but I still gotta set the previous nodes to null, right? So if this was a doubly linked list, I could easily do that by saying tail prev and then set that to null and cut it off easily, right? Otherwise, I can delete the tail, but like, I'm gonna have a dangling pointer, right? Now, the people that said O of n, they could be considered that, or they could say there's no tail pointer, so I gotta traverse the entire list. So, the morale of this tricky question is that you always have to state your assumptions when you're trying to solve an asymptotic complexity problem, okay? So I could ask you something like that on a test. In fact, I probably have in the past. And you have to specify when you give out an answer, when you say O of n or omega of 1 or whatever you're saying, you have to list any sort of assumptions that you've made, such as there's a tail pointer that we can use. It's a doubly linked list, if I don't say which kind of linked list it is. Or there is no tail pointer, so you have to look at the whole list. It's important to make those assumptions just to make sure that everybody's on the same page. Okay? So that was the purpose of that. So, and I also wanted to see how many people were actually actively watching, because so 18 people, so basically about 50% of the people. The other ones are probably just mining points or something. I don't know. So, yeah. Okay. So that's linked list for you. That's all I gotta say about that, pretty much. Let's see if I have anything on my notes here that could be useful to know. Not really. Oh, I do have this part here. I'm just gonna copy and paste this. I don't feel like writing it. Something kind of important to point out, since we just talked about dangling pointers. So this is something that I wrote in the spring 2020, but this time around I'm just copy pasting it. So I guess I was talking about deleting, and my guess here is that this is bad because you're accessing a dangling pointer. So yeah, when you're deleting from a linked list, you will want to do something like this. You'll be like, I'm just gonna loop through everything and just call delete on each of the nodes as I go on. The problem with doing this is between this line of code and this line of code, you are technically accessing a dangling pointer because you called delete on cur before you did cur next, right? So that's bad. It will probably run most of the time, but that one time it won't run and it's going to break your program, right? In fact, I was just doing 202 earlier and talking about the dangling pointer stuff, and I wanted to show them that it's not always bad, but literally every time I try to run the program, it would sec fault. So it's like things never work the way you want them to. But anyway, this is the way to do it. So make a temporary pointer where you copy cur, and then go ahead and update cur, but you still have the old cur in the temp pointer, which you can delete safely. This is the not dangling pointer, healthy version of the code versus this, okay? So this is like your destructor or just a delete function of things like that. So yeah, just something to point out. All right, so okay, moving on to stacks and queues. So there are multiple data structures that we're going to cover, but stacks and queues is one of the most important ones because of how often it's used, right? And so you may have covered stacks and queues in one way or form in 202. If not, then I'm going to cover at least conceptually how they work, but you will have to figure out the coding side a little bit on your own, but it's not too bad. Anyways, so let's start with stack, I suppose. So what is a stack? A stack is how your memory is handled, essentially, in the sense that it goes with a last in, first out approach. Okay? So last in, first out. So what this means is, if you think of it like a bucket, I suppose, and you're storing things in your bucket, like you're putting Legos in there. I don't know why I'm thinking Legos, but Legos is what came to my head. So I got a bunch of Legos in here, and I'm going to store the Legos in my bucket. Okay? My bucket is really thin, so it doesn't really fit too many Legos side by side. So they're just kind of go on top of each other. Okay? And they're all blue. Actually, let's not make them all blue, because that will make it confusing. So let's just pick different colors. What color have I not picked? Yellow. Okay, so I got my Legos here, and let's go. All right, so we're gonna put them in the bucket. So I pick up this Lego and I throw it into the bucket, and it lands there. Okay. Next, I'm gonna go ahead and put this Lego and put it in the bucket. One more Lego. Let's put the yellow one in. Okay? So, here's the thing with the bucket. I can reach into the bucket to grab the Legos, but because it's so thin, I can only grab the top one, or basically the last one that I put in. So if I wanted to take out a Lego, I would have to take out the yellow Lego. I'd have to go in here, grab the Lego, and take it out. If I wanted to get the green Lego, I'd have to first take out the yellow Lego and then go and grab the green Lego. Okay? That's essentially how a stack works. So the last thing you put in is always the first thing that's available to take out. And the first thing that you put in is always the last thing that you can take out. So the first thing that I put in was the blue Lego. That's like way down at the bottom. There's no way I can reach in there without first taking out the yellow or green Lego. Okay? That's essentially how a stack works. What are stacks useful for? There's postfix notation. That's also called like Swedish or Dutch notation. I forgot. Shoot, Google time. Swedish or Dutch? I think it's Dutch. Postfix notation, also known. Oh, Polish. Reverse Polish notation. Yeah, so not Dutch or Swedish. Fail. So yeah. Reverse Polish notation, also known as Polish notation or simply postfix notation. Yeah. So maybe I should write that down. My Polish friend will be mad at me. So, yeah. Okay. So that's one way of adding, for example, where if you have something like 2 plus, and then maybe like 5 times, how this gets evaluated is you go ahead and you put the numbers in a stack, and then evaluate them as you see operators. So for example, you see, and let's just say that each of the numbers is just one single digit long, okay? Because that's the thing. You have to separate the numbers, because like if it was 22, this thing would break. It can be 2, or you have to comma separate them or something, okay? So anyways, let's say that you, let's actually put in one more operation in here. So like maybe let's put an 8 and a plus, okay? Yeah, all right. So, yeah, that should work, okay. So what you do is you insert any number that you see, or also known as operand, into the stack as you go. So first you put in the 8, and you're here, and then you move to the next thing. So you put in the 2, and then another 2. So let's just put 2, 2. When you see an operator, like a plus sign, what you do is you pop the last 2 things out of the stack. So let's talk about some terminology here. The 2 main terms that you should know with a stack is push and pop. There's also top as well. Push is inserting into your stack, and pop is, as the name implies, popping out or taking out of the stack. Top is just a function that typically allows you to see into the stack without taking it out. But potentially, you can implement top as a combination of pop and push. Basically, pop, look, and then push back in. All right? Those are the main ones that you want to think about. So anyways, when you see the plus, what do? You pop the last 2 items in there. So you pop, and then that's how you evaluate that. When you evaluate that, you push the solution into the stack. Okay, and then you keep going. So what's next? We have a 5. So push in the 5. Next we have a times symbol. A times symbol is an operator, so it means pop the last two things and put them together based on that operator. So 5 and then 4. 5 times 4 is 20. Push the result into the stack and then move on. We see a plus. Pop two things, 20 and 8. Add them together. Push the result into the stack. Then we see we're done. When you're done with the expression, whatever is left in the stack, that one item, it should always be exactly one item. Otherwise, it's an invalid expression. Such as, like, imagine if you had a math equation that was like 2 plus 2 times, like that. Like, what would that be? Like 2 plus 2 is 4, but you can't do that because you get to the times part first. But like 2 times what, right? So that would be an invalid equation in like regular notation, right? In postfix notation, it would be invalid because there would be more than one thing on the stack, or basically nothing on the stack, right? So because we have one thing on the stack, all you gotta do is pop it, and that is your final answer to the expression. Okay, so that's postfix for you. Prefix, same thing, just flipped, and yeah. So that's one good usage for stack. The other one is, of course, memory. Main memory you can think of. You have stack variables and you have dynamically allocated variables that are stored in the heap, right? The reason why you use a stack system in this is because some programs are heavy stack memory and some are heavy heap memory. And so suppose you got 4 gigs of RAM, okay? If you got 4 gigs of RAM, you could say, okay, 2 for stack, 2 for heap. But then, like, if you have a program that takes 3 gigs of stack or 3 gigs of heap and like no stack, then it won't run in that computer. However, if you just say, okay, we got the 4 gigs and they're shared, but the way we share them is the stack will grow in this direction and the heap will grow in this direction. So if you have a program that is like very heap heavy, you could end up with something like this that takes like 3 gigs of heap and 1 gig of stack, and that's perfectly fine. Or vice versa, you could have like almost all 4 gigs of stack and like no gigs of heap and still be okay. This is a much better system, right? But the way it actually gets implemented is with a stack data structure, because you keep stacking things on top of it. It's like you put the Legos on top. And as long as these things don't crash or, you know, override each other, you're fine. If they do, you get a stack overflow. So yeah. Anyways, those are basically usages of a stack that I can think of for now. The 2 ways to implement a stack in C++ that you can do so far is you could implement it with an array or with a linked list. With a linked list is very, very easy, because all you gotta do is you can consider like the linked list to be your stack, and then if you are inserting something, you can use your head pointer to point to the top of the stack essentially. Okay, and when you insert something, you just insert it at the beginning using the same function that I showed you before, and you're good to go. And just update the head to be that. In fact, I would rename the head to be called the top. Okay, that's how you implement it. On the array side, it's a little bit trickier because you have to worry about the size of a stack. There's a certain limit, right? Because you got to consider that. The best way to implement it is just to declare an array of a certain size, and then keep an integer that is holding an index. It's not a pointer, it's just an integer. I guess you could make it a pointer if you really wanted to, but I would discourage you from that. And set that index to be 0 in the beginning. What it means is the index will always point to the next available spot in the stack. And so, for example, if you have an array of like size, however spots I can put in here, so 2, 3, 4, size 6, yeah, and then you have nothing in it, then you would put in a 1. So like, let's say we're doing the same example as before. So we got 822 plus, right? So you would put the 8 here, the 2 here, and the 2 here, and then the index will be pointing, every time you insert, you plus 1 it will be pointing there. And so you know that that's the next spot to insert. And it also is very convenient because it'll also tell you the size, right? Because that index here will match the number of items currently in the stack. Well, that's pretty neat. So that was how you would implement a stack with an array. Are vectors based off of the stack data structure? Vectors are dynamically allocated arrays. So vectors is essentially just a regular array that's dynamically allocated with new, but there's extra functions involved that do the magic behind the scenes, so you don't have to worry about like resizing and things like that. However, I do see what you're saying, because like the pushback function is the one that you use to insert things into a vector, and you see the word push. It probably did originate the concept of like from stacks, of the word push to mean insert. But and you could totally implement a stack using a vector and just use the pushback function to put at the end of the stack, and then a remove function with the last index to pop out of the stack. So yeah, fair enough. Good connection there. So do you guys understand basic implementation of a stack and in a linked list or in an array? There's not too much science to it. There's more science with the queue, which is why I started with the stack, because we won't get to the queue fully today. So I shall update this no sorting today. I do still want to start introducing the queue, since we still got 4 minutes. But unless people have questions about the stack. And if not, then I'll introduce the queue next time. So are there any other questions on how a stack works? Actually, let's before we instead of talking about the queue, let's talk about the asymptotic complexity of stack operations within the queue, within the linked list or an array. So we still have the insert and the remove operations in a stack. Accessing isn't really a thing, because there's a top, like you can peek in there. There's a peek function technically, but it's not really part of the purest stack per se. Peek function allows you to see into the stack like deeper, so it's like kind of like X-ray vision into my Lego container, but it's not in the purest sense of the stack. So anyways, what will be the asymptotic complexity in a linked list version of a stack and an array version of a stack? So it turns out that inserting in a linked list, as we saw already, same problem we did, insert at the beginning, and you guys told me that it was omega of 1. So you are indeed correct that it's just O of 1 to do it, to insert. Also omega of 1, technically speaking, as well. Every single case is O of 1 in this scenario. For removing, it's the same situation as O of 1, and so is omega of 1. So they're all O of 1s. For the array, it's always going to be O of 1 for the removal, but technically speaking, for the insert, it's going to be omega of 1, but it's going to be O of n for the big O. And that is going to happen in the special case, because again, you got to make those assumptions that you got to resize the array to fit it. So like if you suppose that you're pushing another number, another number, another number. Now you gotta push one more number. Well, you have no more space left. So you gotta actually make a bigger array, copy everything over, and basically then insert it. So that would be O of n in that special case. But if you don't allow, resizing, if you just say sorry, it's full, not allowed, then it would be still O of 1. Okay, so there's that big assumption that you gotta make if you allow resizing or not on the fly. So yeah, that's pretty much it. Next time we will be talking about queues. We will talk about 3 versions of a queues, technically 2. There's an array version of a queue, and then there's a linked list version, but the array version is boring and lame, so we make it cooler by making it what is known as a circular array, which is the one that will take a little bit of time to go over, and I will actually spend a little bit more digging into that one, because that one's actually good to look at, and you might have not ever seen that before, so we'd actually show you some code and whatnot, and then from there we will go into sorting probably for the rest of the lecture. What if you wanted to get the bottom element of a stack? See, that's the thing, you shouldn't be able to, I shouldn't be able to reach into the blue Lego without taking out the yellow or green Lego first. I cannot go in there. You have to pop everything out. Yes, you are correct. So we don't really include it under the remove, because really remove for stack is always going to be top. But if you wanted to list something like empty the stack, then that would take O of n time, I suppose. That would be the asymptotic complexity of O of n if you wanted to pop everything, I suppose. So, yes, push and pop. So, anything else? Any other questions? Now is your chance. Well, it seems like there are no more questions. So if you have anything else, you can always reach me on the usual methods. So if that is the case, then I shall end the stream. So thank you for watching. I hope this was a good review about linked lists and a little bit about stacks. And we shall pick up from here on the Wednesday. So have a great day. And oh wow, we got the first person to redeem extra credit points already. For cool. Make sure you DM me who you are, like your full name, so I can find you on Canvas and add those points. But all right then, I'll see you guys on Wednesday. Take care. Stay safe. Bye.